Well, let's start to think about getting started here, folks. This is meant to be an interactive and transformative session where we are going to dive a little bit into industrial decarbonization. So I really wanted to encourage folks right from the beginning of this to keep in mind, to keep that in mind, that we really want to have a bit of a sort of an interactive session. So as we go through this, please use the chat function to ask questions, and we'll see how this goes. We'll answer some questions along the way. We'll get a little bit of conversation from some of our participants here, and let's just do a quick round of introductions. I'll start, and then hand it over to some of my other colleagues today. My name is Joe Cresco. I'm the Chief Engineer in the Advanced Manufacturing Office in the Office of Energy Efficiency and Renewable Energy at the Department of Energy. And so I'll be chairing or hosting this session today with a few of my colleagues, and we're going to get into discussion about industrial decarbonization. And let me just turn this over to Bertie Carpenter from NREL. She can introduce herself, and we'll just go right through a list.
Hi, Bertie Carpenter, NREL. I'm an energy analyst, sustainability analyst here for the last 10 plus years or so, and providing support to the Advanced Manufacturing Office and doing supply chain analysis around these next generation technologies. And of course, now in this space of decarbonization of industry, we are going hard at trying to understand what this is going to take. And so looking forward to this discussion.
Sachin, how about you?
Hi, good afternoon all, and good morning in Hawaii. My name is Sachin Nimbalkar. I'm a group leader for Manufacturing Energy Efficiency Research and Analysis Group at Oak Ridge National Lab. Almost 13 years of experience in the field of industrial energy efficiency. And of course, before joining Oak Ridge National Lab, I actually worked on my master's and PhD in mechanical engineering at Rutgers University. And during my time at Rutgers, I also worked for Industrial Assessment Center there, field manager at Rutgers University. So,
great. And Bill Morrow? Can't hear you, Bill.
Right, someone needs to do that, right?
Seems like.
How about now?
Yes.
Okay, all right, yep. Had to find the mute button. Sorry, Bill Morrow from Lawrence Berkeley National Lab. I'm a research scientist. I've been at Berkeley for about 10 years. I focus on industry and manufacturing sector, energy analysis, decarbonization work. Previously, I've been electricity markets and policy person, working on California's decarbonization pathways project years ago. Prior to that, there was biofuels. I started my career as a mechanical engineer building industrial facilities, refineries, chemical plants, pharmaceutical, paper mills, those types of things. So spanning a gamut of industry to electricity markets to low carbon fuels and decarbonization strategies.
Great. And then Ed?
Yeah, Ed Ryder at ACEEE, where I lead the industrial program. And prior to coming to ACEEE 2.5 years ago, I worked at Dow Chemical for 31 years, including a stint leading global teams to develop the 2025 sustainability goals.
Great. Thank you very much, Ed and everyone. So to kick off this session, I thought I'd share a screen with folks for a moment. Let me just see if I can pull it up and kind of highlight what we'll be talking about today. So can you see my screen? Good. Mm-hmm. So industrial decarbonization is a pretty large, broad, kind of big, gnarly topic, a very difficult to decarbonize sector. really diverse in terms of operations, in terms of the fuel and energy inputs that go into that sector. And so we want to really kind of dive into that today, talk a little bit about the opportunities, the challenges, and the research development needs that are going to be important that for the country to pursue to actually really achieve true and deep decarbonization in the industrial sector. So, sorry, getting some notes flying in the background. So just a kind of a snapshot, and I think people are probably well aware of this, but the breakdown of emissions in the United States, it's roughly a third buildings, roughly a third transportation, weighted a bit more towards the transportation sector, and and close to a third from the industrial sector. And it's about the energy use and associated emissions. And so emissions from the industrial sector, as I mentioned, are challenging because there's a lot of different operations. There's a lot of different subsectors and operations within those subsectors. And if you take a look to the right, you can kind of get a sense for some of the key emitting subsectors in the industrial sector and how much they contribute to the overall emissions footprint of the US or the emissions footprint of the technologies of the industrial sector. So what we're really been looking at, and one of the things that within DOE that we've been tasked to do, Congress has asked us to understand and roadmap out what it would take to get to net zero economy-wide emissions targets by 2050. And that's a big lift, especially given the fact that we have an anticipated industrial sector energy demand growth of almost 30% by 2050, which would result in a pretty significant emissions increase, even with business as usual improvements to carbon intensity, energy efficiency, and carbon intensity. So how do we actually really kind of transform that and break out of that? So we thought, one slide that kind of encapsulates or encompasses some of the road mapping that we've been doing, and is this sort of figure. It looks a bit complicated, but if you think about it as a bit of a roadmap, as a snapshot of a roadmap, you can think about these pillars of industrial decarbonization that you can see sort of on that sort of X-axis and Y-axis labels. Energy efficiency, I think, at an ACEEE conference, we certainly are all sort of well aware and tuned into approaches for energy efficiency. Industrial electrification, as we think about moving forward in time as the sources of electricity, for example, become greener, opportunities to decarbonize the industrial sector through increased electrification will be really an important opportunity and driver. Low carbon fuels, feedstocks, and energy sources, kind of a long acronym, but we really wanted to make sure we were including those inputs, those really diverse inputs that go into the industrial sector. Not only sort of the fuels and energy sources that may be, let's say, natural gas that could be burned for thermal processes, but feedstocks, fossil-based feedstocks that go in, and especially those that contribute to emissions through the full life cycle of the products that we manufacture and put to use in our economy. As we all know, we're really looking at how do we transform our world, all of the demand, the energy production and demand sectors to drive towards net zero. And one of the key things that will likely be needed will be carbon capture, utilization, and storage technologies. So this roadmap, if you think about going from the sort of the bottom and left side and forward in time, highlights input and opportunities that we've received feedback from stakeholders, from participants in a workshop series, through our literature work, through scenario analyses that can get us presumably towards a net zero emissions targets by 2050. And so with that framework, I want to kind of like let some of our panelists today start to discuss some of the challenges of doing that. And one of the challenges that we've seen, I'll just kind of kick this off a bit. One of the challenges we've seen is that these sort of pathways are not independent from each other. There's really a lot of interactions and sort of interdependencies between different pathways. For example, when I mentioned industrial electrification, it's certainly relatively clear that the energy sources that provide the electricity for the industrial sector would need to be well decarbonized. But there are other, maybe not so obvious interconnections between these, and I'll let them, some of our panelists talk about those, that different authors from some of the different sections from the industrial decarbonization road mapping work that we've been doing. And so with that, let me turn it over to who is going to, I can't recall who was actually going to go first today. Was that you, Sachin?
No, Ed generally goes first. He's our leader.
Sorry, Ed. Okay, Ed, let me turn it over to you and you can give a little bit of feedback.
Okay, thanks, Joe. That was an excellent intro. And the landscape of challenges certainly is one that we see in the chemical sector. As we think about those four pillars, the industrial electrification is one that's particularly interesting in the chemical section for a couple of reasons. One is electrolysis to generate hydrogen, or the use of electricity to make different chemicals is an area where there needs to be a resurgence in RD&D. Electrolyzers for producing hydrogen need to be much more efficient, which would help to bring down the cost and to help lower some of the big adoption hurdles in that space. But the use of electricity efficiently is also important in other areas. For example, if you think about a steam cracker today that runs on natural gas, if you were to try to electrify that, one of the big hurdles you have to address is making the use of electricity at scale in a huge cracker be really efficient. So you need really good energy transfer and other kinds of things. Just not there yet today. But you see several companies going after an electric cracker. So there's definitely opportunity there. Second, I'll mention in the chemical space is separations. Separations still counts for about 50% of the energy spend for process portions of chemistry. That is separating various components, not only at the front end, but more importantly at the back end of chemical reactions. Will still continue to be a big opportunity. Last, I'll mention energy storage. So that'll connect with some of the things I say relative to cross-cutting, but for chemistry, it's a particularly interesting angle because chemistry can have solutions in this space. Various chemical processes can act as the way to store energy. For example, hydrogen, when it's made, can be stored. Various products such as methanol and ammonia and hydrazine can be any energy storage vehicles. So I think storage is an opportunity as well. And for all those, it's super important to take what we've got as far as technologies and apply them that are low carbon. So there needs to be some applications, RD&D. And second, I'll note that for emerging and transformative technologies, we also need to bring those to scale. So commercial demonstration is also important in that space. But we saw in the chemical area several cross-cutting themes that I'll mention. I'm sure my colleagues will also mention them and reinforce them. The first being process heat. Process heat counts for a huge amount of the energy spend in the chemical sector, as well as several other sectors. So that's a big opportunity to develop and apply a portfolio of process heat solutions. Second, I'll mention efficient production of low carbon hydrogen. So again, that connects with the electrolyzer story. Third, I'll mention is efficient use of variable electricity. So wind and solar is good, and the chemical industry as well as others have been picking up power purchase agreements. What's even more interesting is for the chemical industry to use directly some of the variable power. For that to happen, we need advances in control technology the ability, again, for storage, the ability to control demand response across the chemical industry so that we can most effectively use electrical power when it's at a rate that's advantaged in this space. So multiple opportunities in the chemical space. Let me pass it on to who's next.
Yeah, I think that's me. Thank you, Ed. And I think Joe and Ed, your introduction and whatever different points, important points you covered, that are actually going to help me with iron and steel sector also. So iron and steel sector, by the way, almost 70% of steel produced in the US today is using electric arc furnace approach, and remaining 30% using integrated steel approach, where we use blast furnaces and basic oxygen furnaces. So that is kind of positive news, because almost 70% of steel production is already kind of electrified. Now, if you look at electric arc furnace operations, low carbon electricity, and then whatever downstream operations, once you produce steel using electric arc furnaces, reheat furnaces, annealing furnaces, somehow electrifying those and also using low carbon electricity may solve a significant decarbonization problem in electric arc furnace operations. There is actually a major issue, like for example, why we are not able to recycle 100% of scrap, why we are not able to use 100% of scrap in iron and steel industry and take care of our demand. We cannot actually do that for two reasons. One is copper, tin, a lot of actually impurities in recycled steel, and so we probably need to develop technologies to purify, remove those impurities from scrap when we melt. So copper and tin part, and then second, we also need high quality steel for certain applications. So we need to produce virgin steel. And so, so electric arc furnace operations point of view, there will be increase in EAF operations, and so low carbon electricity is going to help us. Now, integrated steel plants, we have major issues there. Number one is low profit margins, right? Global competition, steel is actually very low cost, but very emissions point of view, very problematic material. And then steel industry requires significant initial investment, and we already have significant existing capacity, almost 20% more than demand. So as newer and cleaner technologies become available, we will be thinking about replacements. That means basically reducing our existing capacity, which is actually very more like dirty blast furnace, basic oxygen furnace operations, and then replacing with cleaner. So we're basically, iron and steel industry point of view, will be facing different challenges. Now, integrated steel making process point of view, there are definitely three major pathways. Energy efficiency is important. We can do things now. That's very foundational pathway, and it is important. But then electrification, low carbon fuels, and feedstocks. And Ed already talked about issues with electrification, availability of low carbon electricity, and then low carbon fuels point of view, hydrogen, efficiency of electrolyzers, availability of green hydrogen. Now, if we start using hydrogen in iron and steel operations, transportation of hydrogen, storage of hydrogen, what happens to the pipelines, burner design, flame temperature, combustion efficiency, we need to deal with all those issues, right? And then, of course, carbon capture, utilization, storage. I think there are two major pathways. They actually look very transformative, but they won't be available until at least 10, 15 more years. One is electrolysis process to produce iron. So, for example, Boston Metals. So scaling up that Boston Metal electrolysis process is going to be very challenging. DOE invested a lot of funds in developing that technology, and today actually that technology is actually going in right direction. Still, it will take a lot of time, Good thing about that technology is rather than producing CO2, you will be producing oxygen, and then of course iron. And then second major pathway to decarbonize iron and steel industry, what we heard from people from industry, hydrogen. And then of course, we heard from Ed issues related to hydrogen. So I think it is possible. In general, it is possible to decarbonize iron and steel industry by 2050, but we need to heavily rely on transformative technology. Energy efficiency will take us closer, and then electrification will help us, but still transformative technologies are needed. All right, Birdie or Bill?
And actually, I think we've had a couple of questions in the chat that just came in. So kind of to help keep this kind of moving back and forth a little bit, maybe Joe, we can try and take a couple of those, one for Ed and one for Sachin.
Sure, let's do that.
All right. Ed, there was a question from Patrick. As an academic chemist researcher, I feel we're quite a long ways from finding ways to do electrocatalysis, whether it be hydrogen or other electrosynthesis in an energy efficient and scalable manner. Is this viewpoint wrong, or are there industry secrets I don't know? Good question. I'm a big believer in technology progression curves, but are we banking too much on future evolutionary electrocatalysis and hydrogen production methods when decarbonizing is becoming more urgent all the time?
Yeah, it's a good question. I would say that, yeah, there's probably a lot of industry secrets that are not out there. That's the reason why they're secrets. I think there has been progress in the electrochemical reduction of CO2. That's one of the main targets. NETL has a program, National Energy Technology Lab has a program called OPUS, looking specifically at this space. But I think we'll also need to recognize that electrochemistry in particular has been a strength of the chemical industry going back probably 40, 50 years ago. That's where chlorine has come from, is electrochemistry. Dow Chemical, where I used to work, started actually from electrochemistry, the formation of bromine from brine. So I think for chemical industry, returning to our roots is an opportunity in that space. The challenge there has been economics, and the cost of electricity is higher than the cost of natural gas. But for specialized processes that can become efficient, I think that's an opportunity. So to answer your question relative to CO2, let's talk about hydrogen. There's a number of groups that are working on improved electrolyzers, and a number of projects, particularly in Europe, that are announcing large scale hydrogen projects. There's also a couple in the US. Plug Power has a couple of projects. The Port of Los Angeles has introduced projects specific to hydrogen. Going back to your electrocatalysis question, I think much of the work that's out there is at relatively small scale. And it's a question for industry to pick it up if it looks economic. And I think certainly some of the drivers that were talked about earlier today, relative to sustainability, that will help to encourage industry to pick that up and to look at opportunities in that space a bit closer.
Awesome. Thanks, Ed. And maybe Sachin, we'll shift to the question to you from John McHugh. Can you speak to amorphous steel production in the US? The lack of sufficient production has been a barrier to high transformer efficiencies in the last DOE rulemaking for transformers. And that affects all electrical usage.
That's actually a very interesting question. I think maybe, John, you could elaborate a little bit your question, but my understanding is amorphous steel, actually amorphous steel is actually an alloy of iron with boron and silicon, right? And it's very specific applications. Could you please maybe elaborate your question a little bit more?
Sure. Can you hear me?
Yes.
Yeah. Yeah. My understanding is amorphous steel has less hysteresis effects, and that has been key to, eking out the last few percent of efficiency gains in transformers. And, DOE, when they look at updating their efficiency regulations, part of the, consideration has to do with the effect on American industry. So my understanding is that we ended up at several efficiency levels below what was optimum. One had to do with not only just amorphous steel production in the US, but even just some of the more basic sorts of things associated with the mitering of edges of transformers versus butt welds and things like that. So we ended up with a relatively low efficiency level for transformers, and so, I'm just wondering if there's some synergies between electrification and decarbonization of the steelmaking process and having, higher quality steels, so that if you have a higher quality steel, then potentially you've got a little bit more headroom in terms of the cost of production. Thanks.
Right. No, thank you, John. And I think, this actually also supports that integrated steel operations, they will not actually go away, particularly if you are trying to produce a very specific, applications point of view. If you are trying to produce high quality alloys or materials, like for example, this amorphous steel for specific applications, we need to rely on virgin iron making process. And then of course, once you have iron, sponge iron, then alloying in, elements and using electric arc furnace operation to produce those specific materials. And so whatever technologies are applicable to decarbonize iron and steel industry, particularly iron making process, are also applicable for these alloys. And so definitely, makes sense. Now, we didn't, during this report to Congress, we didn't actually discuss production of specific alloys or issues, challenges, electrification, related challenges. We mainly stayed on iron and steel, basic iron and steel industry level. Yeah. But thank you for that question. Yeah.
And I think that gets us up to speed with questions. Maybe, Bill, we can shift to you.
And before Bill mentions, I just do want to maybe just add a little bit to the comment. Yes, the session, of course, we're talking about industrial decarbonization, but within my office, the Advanced Manufacturing Office, pursuing those like high value technologies and products that are impactful not only to the manufacturing sector, but beyond the manufacturing sector. So things like AMO has funded for a number of years a program called Next Generation Electric Machines. And so I think, amorphous steels would be valuable in some of those next gen electric machines. And you can do a little bit of, Googling and find some of those efforts. But just to let people, be aware that whether it may be products that are, like next generation semiconductor manufacturing based on wide bandgap semiconductors, or the next generation of electric machines. These are technologies and perhaps shifts of industries or even different industries of the future. And so what we have today, commodities production that has a big footprint. We also have to think about what, where the production we have can provide value to manufacturers and even anticipate tomorrow's energy and emissions intensive production. So if we think about lightweighting vehicles, for example, carbon fiber reinforced plastics are a pathway to doing that. But the manufacture of carbon fiber is incredibly energy intensive. It's about an order of magnitude more energy intensive than steel production. So we have to kind of keep some of those things in mind, not only what we have today and the way we make it today, but anticipate and work on the emerging industries as well. So anyway, just a quick insertion there on that question.
Should I start? Or okay, yeah, and I think the petroleum refining sector and petroleum refining is sort of the crossroads of a lot of other sectors transforming, in addition to its own sector transforming. You know, if you think about it, there's upstream crude oil production. It comes in, gets refined into transportation fuels. Some of it becomes, you know, fuels that are used in other industries. Some of it becomes petrochemical feedstocks. And some of it is self-produced to fuel the refinery itself. You know, a barrel of oil will naturally fractionate into distillates and kerosene and gasoline. And you have the unit processes that transform those ratios to tune them to different markets. And you have the hydrotreaters, you know, that make them able to meet specs. Then you have the lubricants that go to separate markets that are used all across the economy, not only in manufacturing, but, you know, across in transportation. And so how refineries, you know, see a pathway forward is, to me, a fascinating question. Their market is primarily driven by liquid transportation fuels. As we look at holistic, you know, economy-wide decarbonization strategies, there's for a fair amount of push towards electrifying transportation, especially light-duty vehicles. Heavy-duty vehicles are a little bit more difficult to electrify, but it is feasible to do. Your aviation, it's going to be hard to electrify that. So you tend to think there's going to be a liquid transportation fuel. But if each one of those electrify, it changes the ratio of the demand of fuels coming out of the refineries. And refineries would need to make adjustments. If you hypothetically take away gasoline, then what do you do with that portion of the barrel of oil? So then those are, you know, the market constraints that are outside of the decision-making ability of a refinery. There's also this question of if those sectors that, you know, in transportation that need liquid transportation fuels also need to have low carbon fuels, then those low carbon fuels should be made or conceptually made through the refinery sector. So then the refinery sector is looking at upstream where to get low net carbon emission fuels or feedstocks to transform into low carbon transportation fuels, in addition to decarbonizing themselves. And so how the refineries can potentially approach it, well, there's a lot of the technologies that we've covered so far, especially Ed in the chemical sector, that port over into refineries, you know, separations, distillation efficiencies, you know, revamping heat exchangers, looking at ways to more efficiently produce process heat. But the additional nuance for refineries is the self-produced fuels, still gases. Those are collected throughout the refinery processes, collected together and largely fuel the furnaces and the CHP units, the combined heat and power units in refineries. Those combined heat and power units supply a fair amount of the electricity that is used inside a refinery, as well as some exports to the electric grid and then purchases from the electric grid. There's a fair amount of natural gas that comes in. Hydrogen gets used, you know, through a steam methane reformer, pull out the hydrogen. There's a CO2 emission right there. Some of it is burned in furnaces. But changing the mix of electricity to furnaces adds another complexity constraint, because refineries are highly tuned for that fuel mix of furnace, you know, fuel consumption in furnaces and electricity for motors. There's still some steam generated pumps, for example, that could be converted over to electricity, but they tend to be there because there's excess steam. So changing that balance of how energy is used in the refinery in order to accept like renewable electricity as a substitute. Finding a solution for what to do with the still gas becomes a big question. Converting one set of, bundle of technologies efficiencies, like say process heating, would then affect what you're doing with the still gas, affect your CHP loads or what you're selling. Would you be able to sell excess electricity back to the grid if the grid is decarbonizing? So what are the strategies? The refining industry sees it as, well, I'm not a refinery person, but my understanding is, see it as largely driven by markets that they have no control over. What they do have control over is technologies inside their own units. And so there are strategies where, we've mentioned some of the technologies before. There's larger strategies of, for example, taking natural gas and taking out the hydrogen and burning hydrogen in the furnaces and capturing all the CO2 at one large steam methane reformer, if you will. That is probably more cost effective than putting carbon capture on all the furnaces, because there are large furnaces and small furnaces. Putting carbon capture on furnaces inside a refinery, you want to go for the larger CO2 emitting sources. And there you have some large unit process units that consume the bulk of the energy and produce the bulk of the amount of CO2. And so it's feasible to, capture CO2 with what you're not able to, or the CO2 emissions that are remaining as you ramp up your efficiency through revamping your refinery. How the low carbon feedstocks will come about, once again, is outside the refinery's purview. But one thing that they can do is the CO2 reduction pathway that we've talked about, that Ed had mentioned. And at the end of the day, there's a large market of liquid fuels that will probably still be remaining for quite some time to come. And so providing fuels to that market as that market is decarbonizing is perhaps one of the ways that there's more fundamental science and R&D within the refinery sector of getting their unit processes to accept a yet unknown feedstock, having a way of tracking and understanding and having confidence that an alternative feedstock does actually get a CO2 reduction credit. If it's a bio-based feedstock versus like a collected plastic that has been broken down into, a hydrocarbon feedstock, refineries feel confident that they can make that into a liquid transportation fuel, but what is the supply going to be? And so doing the R&D in the refinery industry, I think, has a lot of parallels with what we've talked about with chemicals, with a lot more uncertainty about what markets and policies, both in the United States and globally, are going to ask the refinery industry to do. For that reason, I think it's the most exciting sector to think about, because it connects the electric grid, fuels, decarbonizing other sectors, as well as decarbonizing itself within the industry. And I'll pause there.
Well, you have a couple of comments in the chat, maybe that you can respond to, Bill. I can read them, or if you're able to see them, maybe.
Yeah, read them.
On to Gail and Neil's comments.
I can't, I don't have the chat thing open.
No worries. So Gail commented, if we succeed in electrifying transport, then refineries are reduced to making chemical feedstocks. Essentially, they'll shrink, or maybe make jet fuel. And then related to that, Neil also commented, we already see refineries closing in the US as demand reduces. Do you see the mix of products changing in the future?
Well, the answer is yes. I know that I have participated in debates with, refinery folks for a number of years of, if we're electrifying transportation, wouldn't we just shut down the most inefficient refinery one by one as the demand decreases? There's some, reasons to believe that that's how the industry would respond. Some of those refineries tend to be tailored to markets that they are local to, taking in specific crude they're accustomed to. So then you would still need to satisfy fuels into those markets. But that is a realistic way to anticipate the industry reacting. But ultimately, staying in the we will survive into still an energy supplier, I think is the best strategy and the most optimistic strategy for the refining industry, with a lot of uncertainty about what the demand and markets are going to do, and high probability that there's going to be shrinking markets. The choice to invest in very expensive carbon capture technology, let's think of a way to find the incentives, I guess. I don't know the answer.
Or they become hydrogen producers, or maybe renewable companies. So
right, yeah, and I know that there are some of the majors that look at it from that perspective. That they will become energy carrier suppliers.
Yeah,
like renewable hydrogen. But if you can take a captured CO2 molecule, break it down, and pull out to a CO, and put some hydrogen with it, turn it back into a liquid transportation fuel that we're accustomed to, you've already got the infrastructure and the pipelines and everything to handle it. So that's where I tend to see CO2 reduction as being the technology that opens up, a strategy to have low carbon hydrocarbon or low net CO2 emission hydrocarbons and keep our infrastructure that we already have.
So there's a follow-on question from Patrick. Is there a world where natural gas still largely exists if we can separate hydrogen and capture, utilize CO2, effectively making a closed loop fuel resources powered by renewable electricity catalysis?
State the question again, because it may have gone in the direction that I was expecting it to go one way.
Okay. Is there a world where natural gas still largely exists if we can separate hydrogen and capture, utilize carbon, effectively making a closed loop of fuel resources powered by renewable electricity catalysis?
That would be the ideal. I mean, whether it's coming from natural gas or whether you're getting the CO2 from natural gas or you're getting it from other industries, I tend to think if we're going to have process CO2 emissions from cement and iron and steel, that would be your source of your CO2. Getting the hydrogen from renewable electricity and water electrolysis would be the pathway for that. So I see that there are feasible solutions where the refinery industry is alive and well and profitable. So yes, I mean, that I think is the optimistic goal of how refineries play a role in helping the whole economy decarbonize.
Yeah.
And get a steady state, net carbon balance.
Yeah, even in iron and steel industry specific discussion, at least few industry people, they actually mention use of natural gas in directly reduce iron, DRI process. We continue doing that and then use carbon capture, utilization, storage, other side. And then that way, we can achieve both, like use natural gas and at the same time, carbon capture, utilize, storage. So even other sectors, similar.
And, if the whole entire economy is decarbonizing and the demand for natural gas and oil is decreasing, you would tend to think that the prices will collapse and get cheaper so that there would be an abundance of the natural fossil fuel supplies. I'm not going to speculate on whether there would be a carbon tax or not, but that would provide an incentive to do natural gas, steam methane reforming or something, and using the hydrogen, capturing the CO2, sequestering it, because it would be inexpensive fuels.
So there's a
With a
question
carbon
from
tax, you
Austin
put the flavor back in the can.
about maybe what has California done, and you may have some perspective on this. How has California approached the refinery industry under its cap and trade and clean fuel standard? Has the state tried to promote a transition to cleaner products and practices beyond those two policies for refineries?
Well, I mean, it has a bit of a history. You know, there was the low carbon fuel standard, anticipated to be met with biofuel resources. Looking at the constraints of biofuel supplies, indirect land use considerations sort of made there less confidence that that was a good pathway. There has been interest in a bio-based methane replacement of natural gas in California. And I think there are refineries that are transitioning to a bio-based or a low carbon feedstock, you know, to produce a lower net CO2 emission fuel in California. And I tend to think, you know, California leads by example and makes mistakes by example in a way. So there's a lot of experiment with policies and then discovering that it had the consequence that didn't expect. And so changing that, I could imagine that California will remain in that leadership role of the brave state that goes and learns the mistakes. But ultimately, you know, if you try to satisfy our petroleum demand with a bio-based feedstock, you run out of land well before you can satisfy all the fuel demands. So there has to be some way of lowering the overall demand for transportation fuels. And that's where naturally electrification of transportation comes in. I think California is aware. Electrify the transportation fleet, light duty fleet first. But there'll probably still be liquid transportation fuels. We're still going to fly airplanes.
So this maybe really is related to Prakash's comment. What share of US refineries serve the US economy versus serving a global demand? And if US does electrify, could those US refineries still have significant demand from that global market if the rest of the world is not also simultaneously decarbonizing?
Well, and I don't know if folks on the call know Dr. Sokolow at Yale? No, Princeton.
Princeton.
But a number of years ago, I had an opportunity to just meet him and chat a little bit. And I was thinking about, at that time, what happens if we do electrify transportation and the price of oil goes to zero, essentially, or, you know, very cheap. And his answer was, well, of course, developing countries are going to use it. That's why we need to develop the technologies that can leapfrog it. The use of the very, very inexpensive oil. And I thought that was probably the best answer that anybody could make. All the more reason to develop clean technologies. Because I would expect other countries in developing areas to use very inexpensive oil if the United States and Europe and Asia's demand for it goes away. What do we do then? I don't have the answer, but it is a known question. But I think technology, keep developing the technologies. That's the purpose.
And I guess part of the perspective that we've also been trying to work with is that ideally speaking, we'll be able to kind of lead the way on developing these technologies, you know, in the US, and that can be adopted and deployed elsewhere to get everybody else to where, hopefully, where we will be eventually.
Right. and actually, that is very, very, you know, good point, Birdie. Particularly if you look at iron and steel industry. If you look at globally, it's completely opposite what we have in the US. So 75% of steel is produced using integrated iron and steel, you know, process, integrated. So coke, you know, coke making, blast furnaces, basic oxygen furnaces, right? 75%, and only 25% is electric arc furnaces. Completely opposite what we have. And so if we actually develop clean iron making processes, like, for example, electrolysis process or hydrogen-based processes, what happens is now, we create, market for our technologies, globally. And also, by the way, there is actually policy angle, regulations angle also, by clean, different borders, and then it will actually benefit our iron and steel producer in that case also. So yeah, and that's not my background, by the way, regulations and policy, but you all know that is actually that is going to play a very important role. Yeah.
Yeah, and I was going to chime
So
in.
this next question from Patrick, actually, Joe, maybe you might be able to take this one. Lots of exciting topics for RD&D in the energy field. How do these organizations promote such research? It took 50 years for lithium ion to get where it is today, but we don't have that time.
That's right. Everybody has to work 24 hours a day. Get busy. It's this is a serious question, and it's I think there are some nuances. The question about, if you look at the full lifespan for something like, crystalline solar, silicon solar PV, or lithium ion batteries, what you see is a, sort of a slower process, and then there can be an acceleration. If you look at, for example, the cost of photovoltaics or lithium ion batteries is a good example in the last decade. The price drop has been just radical. So one of the things that I think that is kind of good news in this space, in this industrial space, is that we are not talking in many cases about technologies that don't exist. For example, the use of electricity in thermal processes is relatively small in the industrial space. It's less than 5% of all energy demand in the industrial sector is electricity. Not 96%, almost 96% is fossil fuel based. It's either direct use of fossil fuels or indirect use, making steam to heat stuff. So we set things on fire to make things hot. And but that 4 or 5% that is out there is at commercial scale. So things like induction heating is out there at large scale, at very large scale. Things like the electric arc furnaces and think about aluminum. Aluminum in the I think late 1800s, early 1900s was considered a precious metal until the Hall-Héroult process came online, drove that cost down. And so what you'll see is this sort of this long time for sort of fundamental science to actually make its way in. But what we can really harness, some of what we can harness out there is that a lot of that work is done, and it's now the job of the world to say, no, we have to move that last piece that might take 20 or 30 years, moving slowly. We can do that in 10 years, 15 years. And I think it's really just it's a political will. It's a will of countries, of people to really say, yes, we're going to do this. And what I think the other good piece of good news is, we are seeing a lot of companies that are not only innovating and pushing these technologies out there and driving those cost curves down, but we're also seeing, I think, a more acceptance of the need to transform, and the realization that has to happen, and willingness to look at some of these new technologies. And the question, the point about leapfrogging, I think that's part of this, which is people are looking out and saying, wow, if these technologies are viable, we're going to be left holding the bag with sort of old technologies. If we are taking materials out of the ground and we're processing them and we're jamming enormous amounts of material into the atmosphere, I mean, that's not efficient. It can't be. And a process that can do that more efficiently without that sort of materials waste has the potential to leapfrog incumbent technologies. And I think that's so I think there's good news within that space, that some of the fundamental science we have underneath it. It does not mean that we don't have low TRL challenges to scale. We do. We still have, scaling, these processes from, marginally sized, small pilot scale to really true commercially viable scale is not easy to do. And that's where investment, it's people talk about this as that one of the many valleys of death. And so, or some of the many valleys of death. And so we need to be able to leapfrog these valleys and get to, get to a more productive future.
Yeah, I actually have a quick comment on this, and I think if we look at process heating, in November, December 2020, we organized thermal process intensification workshop. So what we did is we of course we focused on transformative technologies, out of the box thinking, or even electro technologies out of the box thinking there too. But we also started looking at smart manufacturing, IoTs, to improve energy productivity of existing systems. As we are working on these transformative technologies, it's going to take 10, 15 years. We cannot wait, right? And then at the same time, we also talked about waste heat recovery, recycle, reduction technologies, material issues, design issues, and then research R&D needed to make things happen. But so the point is, as we are working on these transformative technologies, when we know it takes a lot of time, Boston Metal technology, or even this BASP, they are working on this methane pyrolysis technology last 20 years, so we cannot wait. And that's why this audience, strategic energy management, energy efficiency, we need to continue. We need to continue working on those. Yeah.
So Birdie, this is Ed. If I can pick up on a question there from Liz, I think it's kind of interesting that she raised the question relative to demand side versus supply side. And I think one of the big accelerators of progress in this space could be demand side requiring low carbon products, demanding whatever you might put on that, so that industry sees the market opportunity that helps to drive innovation, entrepreneurs, and the demonstration at scale of technologies. So I think it's important to consider the connection between the demand side and the supply side.
Definitely. And maybe on that note, I might kind of pick up a little bit on some additional aspects that were not dug into too deeply for the roadmap. So as we were evaluating, what we could be looking at for industry and where we could be evaluating opportunities for decarbonization, we had, some key industrial sectors that was clear that we could, evaluate in more detail. Sachin talked about iron and steel, Ed talked about chemicals, Bill talked about the refining sector. And then we also had some work done in the food and beverage manufacturing, as well as cement manufacturing. So some really big sectors. But there are obviously a lot of sectors that we didn't cover. And so as I think Ed also noted, there's opportunities for really looking at where are the cross-cutting technologies, how can we leverage what we're learning in some of these bigger sectors or anywhere at all in the manufacturing sector and apply that more broadly so we can get that coverage we need to get to that decarbonization goal. But another aspect that we really didn't cover was anything outside the facility walls, pretty much. So we talked about scope 1 and we talked about scope 2 and the kind of technologies and the strategies we were looking at. Scope 3 was kind of a little bit beyond what we could get our arms around for this particular effort, but there are some really big challenges upstream and downstream of what's happening in the industrial sector. The supply chain, lots of studies have been done to indicate big impacts, big opportunities for reducing total global warming potential and carbon emissions as we evaluate the full supply chain and where can you make changes in your supply chain. And maybe that's partially material substitutions, maybe it's technology transitions, lots of different opportunities there, but we need to dig into that a lot more and understand that better. The other side of that is a little bit of what Liz was talking about, your demand side. What are these products being used for? How are they being used? And there's this discussion about lightweighting. That's a very clear example where we're saying, we're looking at the long term. How are these materials, these products being used? How can we ensure that that has as low of an impact as possible? So you move to LED lighting. That's a clear example of where we're reducing our impact downstream. And in the food sector, this was also one of the clear outcomes. I think there's a huge amount of diversity in the food sector, but one of the areas we found that was, and a lot of the research, Sachin included, has been doing to see big impact in the food sector is at the consumer stage, because it gets wasted and food waste has enormous impacts. So how can we create processes, packaging, labeling to better inform consumers and to ensure that those food products don't end up in a waste stream creating carbon emissions. So I think there's lots of space to be doing a lot of different extra things, but I think we have to kind of start thinking outside the box as well in terms of where those impacts are occurring and where we can take active action in the industrial sector that will broadly have impacts throughout the economy.
So Bertie, if I could just pick up on some of your comments there. We heard in the sustainability panel earlier this morning from GM and Hemlock Semiconductor that they are working with their supply chain partners to lower their emissions. GM, for example, noticed that 75% of their emissions relate to the use of their products, that is cars. So they're, the transition to electric vehicles is part of that story, but GM is also trying to work with consumers relative to education, as well as the structure of the cars. Second thing they noted was that 20% of their emissions is along their supply chain. So they're working with their supply chain partners to not only encourage energy efficiency and the use of energy managers, but also working with their supply chain partners to have them make the transition to renewable energy, low carbon materials where possible. So I think we're starting to see some action on the supply chains at this point in the industrial sector. I mean, we've seen it for years in the sectors dealing with Walmarts and others that they've responded to customer demand. John McHugh's got a question that I saw that talked about embodied carbon. And I think the answer there on whether embodied carbon is truly going to be something that has a dramatic effect, somewhat looking at the response there, but certainly there's strong drive for that. And there's buy clean policies in California, and they've been discussed in several other states at this point. So that's certainly an approach. Still some of the evaluation still out there on the impact of there, but certainly that's one move on the demand side as well.
That's very strongly related to the concept of use intensity that I know Joe has been talking about for many years now, and is closely related to kind of circular economy principles, how you ensure that the products that you produce that have a lot of energy and carbon intensity associated with them, embodied carbon and embodied energy, make sure they're staying in the economy and providing function for as long as you can, because as soon as they go out, then you're creating something new to replace it. And so that's just more energy and carbon going into the economy. So as I think that's the other place where industry can also play a role in just ensuring that the products that they're generating are have a really good, long, useful life and the ability to kind of be remanufactured, updated. I mean, there's a lot of that to see constantly on your computer. Updates are always being pushed through. This is just a way for us to keep these materials in the economy for as long as possible and reduce how much new product and new materials have to come in with which have that embodied energy and embodied carbon associated with it.
Yeah, yeah. I was just maybe a very quick comment. This is, I think, such an important point. And for folks that might not be fully aware of some of what we've been doing within DOE, investing in technologies. historically, our office looked really just kind of closely at, facility energy intensity, things that are happening kind of, within, just very tightly within the industrial sector. And of course, that's still very important, but it certainly doesn't give us the whole picture. And within the advanced manufacturing office, as well as other offices in EERE and beyond, and also in the private sector, taking a more holistic look at a sort of a broader net impact and understanding, and using life cycle thinking, life cycle approaches and thinking, that really can inform us more clearly on where there are opportunities, and really, if we think about the way we've processed materials into products, this very linear process, pull stuff out of the ground, manipulate it with fossil fuels, use it and dispose of it. It's not a sustainable approach to living on planet Earth. I mean, we see this now, and thinking about more circular approaches, reverse supply chains are an incredible opportunity for new companies, new industries to form. How do we actually take materials at end of life and reprocess them? And so that singular thinking really can upend the way that we do things today. But not all reverse supply chains are going to be efficient. Some of them could actually take more energy, to reprocess materials than pulling stuff out of the ground. And so it really forces us to understand, where today are we with sort of these circular loops from end of life. And if we needed to really think about redesign from the very beginning, this is going to force us to say, well, gee, that if we have stuff that we've made in a certain way that we can't use now, reuse, could we make a simple fix at the beginning of a product design, or the choices of the materials that we actually use in our products, such that we can actually change that end of life paradigm? And so those things are all very, very important. And I think I think that's another kind of bit of good news, is that even companies like Apple, I think I just saw this recently, was looking for it, have are changing some of their design, allowing the right to repair your products, so things that were, their business models are actually changing. So Sachin mentioned we've talked about technology and RD&D. Sachin alluded to policies, and we've talked about that with Buy Clean and some other things. But there's also sustainable, sort of the social contract that companies have with us to produce things in a certain way. And so I think people's voice is also really important, and it does drive change. And I think companies are getting on board with this, and they're I think social approaches to sustainable products is another important driver.
Yeah, and then particularly Joe, that addresses Gail, one of your comments too. As energy prices actually going down, particularly natural gas, even if technologies are available, if you look at our bandwidth reports by industry sector, current typical energy intensities and state of the art, that gap is there last 10 years, 12 years, 15 years. Manufacturing plants still there. Why? And so, and then every time we talk with these manufacturing companies through this Better Plants program, DOE's Better Plants program, what we hear is natural gas prices, low energy prices, and whatever you point making there, Lewis Carroll's Red Queen and Alice. And so whatever Joe just mentioned, those are probably few options. Along with technologies, we need to explore policy regulation options too, because same product in New Mexico, and then if we are producing same product in Michigan, why there is significant difference in energy intensities or water intensities? 2 gallons per liter of Coke in Texas, and then say same product in Michigan, it's 6. So what that means is we have technologies, but we are always thinking about cost, those social aspects, how we make it happen, and so we need to think beyond technologies too. Sorry, it's not my area, but I would like to add that comment there.
I think we also could think about the timelines a little bit more and what we need to do today um, to allow us to affect this transition over the course of the next 30 years. So 30 years seems like a long period of time, but it's not. Joe had mentioned accelerators. We illuminated a couple of them, but I think certainly market demand for low carbon products is one of them. Another one is innovative technologies that come along and change our lives. Just think about the fact that this year is the 50th anniversary of the birth of the transistor, Intel. 50 years ago, he introduced the transistor. What a revolution that has been. So I think finding new paths to technology are important, focused on this challenge of decarbonization. So let me just kick off the discussion about what we can do now, near term, midterm, long term, with chemicals. And I would say that in the next 5 years in the chemical space, super important to look at low capital solutions. So energy and materials efficiency fall in that camp. Improve separations and smart manufacturing. Also are things that we can do now. We don't have to wait. There are a number of electric technologies that could also be deployed within the next couple of years. And many are already commercial. Infrared heaters, microwaves, for example, industrial heat pumps are moving along rapidly to new areas of application as far as higher temperatures. And I think we need to change out some of the sources where heavy hydrocarbons are currently used. So some of these process industries are still using coal, coke, and other heavy hydrocarbons. We can change that, right? I think there's also, as you look along the line a little bit further, we've talked about increased use of hydrogen, blending into natural gas and others without changing out the pots and pans. That's something that can be done that would help to speed the transition. I think in the chemical space, I also got to mention green chemistry, because that's a new way of thinking about making the same types of products, and aligned with that, green engineering. And I think looking further out, we need to think about improved efficiency for retrofits within the chemical industry and improved processes for integration. But we can't wait 10 years to think about transformative technologies. As Joe showed that landscape figure, many of these things need to happen in parallel. There's things that we can focus on and really drive in the next 5 years, but we also have to be working on the RD&D, applications RD&D for the next 10 years, and the transformative technologies that may not come along for 15 years. Let me stop there and see how others build on that.
Maybe this is a good time. I know we're coming in within 15 minutes or so of wrapping up the session. And I mean, Ed, I think that's like a really good possible like segue to maybe pose some queries to the to the participants, like within this landscape of technologies that you've seen and you've heard us kind of discuss here, and we've seen some questions. But if we were to maybe turn the tables and ask folks, at maybe your companies or what you've seen, like where might the more likely or approaches be? What are you considering maybe at your company, or if you're consulting or whatever? What are your organizations, and what are you thinking of as technologies that are maybe looking really viable and useful, or maybe there are things you thought of that you just don't think are viable, and why? So, if there's any kind of reactions to that, maybe just, some comments in the chat, or we could open up the mic a bit to folks.
And I think complementary to that, Joe, is based on where they see opportunity. What are the needs for AMO to pick it up relative to RD&D?
Yeah, I mean, it's not just AMO, it's, it's actually the, it's, in fact, I mean, I'd almost take the, several steps back. I wouldn't even say it's just, DOE, it's almost the, kind of the role of government and the role of the private sector here, where, where where does there need to be some really, big pushes to maybe catalyze?
Yeah, and I think as our audience, actually thinking about their thought, they're coming up with their thoughts. By the way, Ed, last few comments, your comments, I think those are very, right on target. And good thing is in our report to Congress, by the way, all different sectors, whatever 5 different sectors we actually studied, and then we interacted with different companies. So we have actually listed all those technologies by market readiness as well as technology maturity, different levels. Ed actually just went over chemical sector, so you will find similar information in that report to Congress. Hopefully, it will be published in the next few days. Back to Joe, Joe's questions. Let's hear from our audience here.
Holly, you had a comment you put into the chat. Maybe you want to just unmute yourself and share your thoughts.
Sure. I mean, it is that, but I am with traditionally a natural gas company, but we are working to become carbon neutral by 2050. And most of that's through hydrogen and RNG, but we're also looking at other possibilities. And one of them is carbon capture in various forms. And so we've come across a manufacturer out of Canada called Clean02, and they have some technology about the size of 2 refrigerators that goes on a 1 million BTU boiler. I think I have that right. And they put in a hydroxide, sort of a catalyst that combines with the carbon from the flue gas, and it creates a bicarbonate that's then used to make soaps and fertilizers. And the payback is really good. So to be able to have something that's near term, cost effective, tangible, I mean, all these things, so many of the things are like ethereal and kind of far off. So to have it like, no, we can go look at the product is pretty exciting. And it's not going to save everything by any means. It's not a product we can apply on all large customers, but we are testing it on some and hoping to make that more, one path that will be helping our larger users.
That sounds awesome. And I just want to kind of connect to that a little bit, because the fertilizer connection, I think, is a really interesting one. And as we are looking to move into this more bio-based fuels, products, and so forth, fertilizers is a huge, huge impact. And to be able to kind of provide that in a more low carbon form, I think is really valuable.
Yep. And actually, we've been working a bit with Denmark and understanding the way they approach carbon reduction. And for them, they're like, you guys get so myopic about this. Like, we're really trying to do circular economy. And it's not just about GHG reductions. It's also about, because they're really into biogas and renewable natural gas, but it's not just taking the RNG. It's also taking the byproduct, the fertilizer that then makes a richer soil. And so just really challenging us to try to think more holistically about the problems we're solving and our solutions, and looking for like more elements that your solution could be providing. There's more solutions than how we're typically looking at it in our siloed American way, I guess.
Yes, we do have to get out of our silos. Mm-hmm. I agree.
Well, I do see that that's opportunities for industries to be created. That what we have today, why would we believe that it'll be like that in 2050? Let's open our minds and allow, innovation to take place. What do we do with the CO2 that we capture?
Yeah, and I think it was really touched on here, this idea of circular economy, even though I don't know if those words were said, but, thinking about the end of life on a product, and if you don't have a good disposal of it, then you better rethink it on the front end. Or if you have something on the back end, then great, we can put it into more of that circular use. So it's just really a different way of thinking, but it's a lot more inspiring to think that way, even if it's harder, but working together, I think we can do it.
Yeah. Right. And I think I'm sure Ed probably knows a little bit more on this. Chemical companies like Bosch, they are actually developing new technologies to actually utilize CO2 and produce something useful. So that carbon utilization is actually more powerful rather than carbon storage and dealing with carbon storage infrastructure and potential leakage and other issues. So yeah, I agree, Bill. Innovative thinking is needed. Yes.
Well, and I'll mention it's not just CO2. There have been research to take CO out of steel plants and to convert that into feedstocks for chemicals. There's some projects along those lines in Europe. I'll pick up on one of the questions I see there relative to investment strategies and timing for companies. One of the challenges in this space is the timing of the rate of return. So several years ago, investor companies got into the green tech space and thought they were going to make a fair amount of money as everybody jumped in to get various green tech. However, what they found out is that the returns were not very good. And so they jumped back out of the area, which kind of drained the investment pool. But various entities have kind of gotten back into this space with the perspective that you have to have a long-term outlook on this. One of those is Breakthrough Energy Ventures that is pushing the longer-term investment in this space. The second component in the question that I read is the challenge of, quite frankly, lock-in. That is, do you invest in current technologies or near current technologies, or do you wait? There's certainly a debate, and I'm sure it depends on the technology, but a challenge in this space is that the CO2 that we emit today, more than 70% of that is going to be in the atmosphere in 100 years. So CO2 is long-lived, and so if you think about the time value of money, there's also a part of the equation that we need to think about, which is the time value of carbon. And so carbon that we reduce today is much better on a molecule basis than waiting 30 years to remove that carbon. So it's super important that we start today, but also with a perspective of the fact that we may need to change certain technologies in the future. Several years ago, as people were building power plants and others, they classified them as being CCUS ready, which means that they had the flanges and they had other parts of the engineering that were adaptable. As we think of new processes, we need to make them so that they can be changed in the future. And the economic pain and the technology pain to change them is a lot less. I think it's part of the design feature. Other comments in that regard?
One of the ways that I like to think about it is that we develop ways of taking CO2 out of the atmosphere, put them into products so well that there's less CO2 in the atmosphere and we need to put some back in to keep the planet warm. That's the way I tend to think of it. Let's make that a goal to where we're cooling the planet too much because we figured out how to deal with the CO2.
Yeah, I think,
Josh, you posted
well,
a comment in the chat. Maybe you want to just go ahead and unmute and share your question.
Yeah, happy to. I'm just wondering if we bank on carbon capture or utilization and kind of don't do the DPE you guys are talking about, electrification, and just say, well, carbon capture is going to be here to save the day. Is there a risk to that? Is there, I mean, if we do sort of a carbon balance, is there enough carbon demand for all the carbon we're going to capture? That sort of question. Or do you guys potentially see any risk? And I guess we saw Cleveland Cliffs today say that, their operations are at global best for steel manufacturing, and now they're doing carbon capture. So I'm just wondering, is carbon capture potentially like this dream folks are hoping will just take care of it? Or do you think it's not, and folks are still going to do these process innovations y'all are describing?
I guess I'll start on that, saying that carbon capture has been around for more than 20 years. And CCUS has been demonstrated at scale, particularly for power facilities, not so much for industries such as the chemical industry, cement, steel, et cetera. So one of our challenges is to demonstrate that. But I think in the studies that we have done, we expressed that the four pillars can work well together, and that energy efficiency is particularly important to push in the next 5-10 years. But you don't stop with energy efficiency, it continues through the next 30 years. Electrification, particularly as the grid becomes greener, is also important to push. It's connected, of course, with hydrogen and other pathways. A study from Princeton, the Net Zero America study, shows that transformation of the electric power sector can really help to transform these other sectors that we're talking about if you can get the wind and solar, et cetera, at scale. But CCUS, since there's very little potential today for economic return, unless you do CO2 enhanced oil recovery, it's one that tends to be towards a mitigation solution. So in other words, push the other three components as hard as you can, but also prepare for CCUS for those circumstances where you can't address electrification or hydrogen or energy efficiency still leaves you with a delta. And in fact, in our studies shows that there's still going to be a delta that needs to be addressed to get to net zero. And that's where CCUS needs to come in, plus other things such as, trees and others, and perhaps, carbon pulled from the atmosphere, direct air capture, and other technologies. I think it's, again, a question that you need multiple solutions in the space. There's not going to be one solution that fits for all applications.
Yeah.
So, others?
Yeah, I think I'll just quickly add, I think this entire carbon balance is really important. And there are other things that are going on. We have oceans, we have forests, we have weathering of rocks. And there's some really interesting, potential with some industrial byproducts that have the potential to, capture, to bind carbon. So, and, to what extent can we fold those back into products to become carbon negative products like concretes, where we're using that as aggregates. But I think, we have to also think creatively about, our, the current sort of, maybe byproducts, processes where we can do, it's almost to Bill's vision of like, I think we need to kind of, maybe go beyond just like, oh, let's attain this one goal. It's like, no, we want a knob that we can really dial further if as needed. And what do those take? And direct air capture, certainly. We are investing. We have research and development dollars now going into a number of direct air capture projects and integrating those sort of into industrial production systems.
Yeah. And I think, in general, Ed and Joe, their answers are always comprehensive. They cover all different angles. Maybe I would like to add one angle here. And I think that angle is we need to actually use LCA and techno-economic analysis approaches to look at all these different options. Prakash, in fact, we actually looking at electrifying clinker making process, right? So if you look at that option, electrifying clinker making process using low carbon electricity. And so what we did is we looked at a current grid, and then we also looked at cleaner options, wind and solar and much cleaner electricity. Even in that scenario also, when you start looking into capacity factor of wind and solar, and then infrastructure needed to build renewables, whatever materials needed to build that infrastructure. And then when we completed that LCA, what it's showing is, GHG emissions point of view, we may actually make some differences, but overall material depletion point of view, not necessarily we are going to win. So same thing with, I think, carbon capture. There are so many options: biological and bio-inspired capture, direct air capture, and then what we do with after that capture, how we utilize it or store it, what happens after that, and then if we actually use it, then what is that techno-economic as well as life cycle analysis in terms of GHG emissions. So that is actually needed. And that's what we are doing, by the way, strategic analysis point of view. We exploring all different angles here.
And I think we're probably at time, but I'll throw one last question out that was in the chat. Can we have a viable CCUS strategy without carbon pricing? That's a goal, but can we actually do it? I guess that depends on whether we can get the technology where it needs to.
And it's kind of what Sachin just mentioned, that there is a techno-economic question there. If that carbon, if the utilization point is the question. I think to me, very simply, if you're sequestering it, and you're paying to sequester it, and you're not getting a benefit from that carbon you've grabbed. You've grabbed it, and but if you can grab it and use it, and it's requiring, it's allowing you to be more efficient with your your entire materials balance. Then there is the potential. I mean, certainly, to get all the way where we need to go, we're going to need some kind of price on carbon. We have to. I mean, I think Gail mentioned in the comments, Boyd mentioned in the comments earlier, he's an economist. And, I want to tell the economists there are no more externalities. Externalities have to go away. We can't say there's externalities. We have to internalize all externalities. As a society, we can't sort of just say, well, that's beyond our analysis. Our analysis has to include, the impacts, the negative consequences for the things that we use. And it kind of goes back to things like the Boy Scout motto, leave no trace. I mean, we really do need to kind of really think about everything we're doing holistically, and and account for those impacts. So I do think there could be some places where I put one link in the chat about an example of one company. There's a number of companies that are trying to figure out how to get that carbon back into their product. And that might really be cost competitive to do that, if that's technologically it could be successful.
Yeah, and the way that I tend to think of a global or price on carbon is, yes, I completely agree with the economists that would be efficient. While we're waiting on the globe to agree to that condition, let's develop the technologies and do a suite of technologies, because there's probably not going to be a silver bullet. There's going to be a lot of silver bullets across a whole gamut of technology approaches. And we need to start and work hard.
Yep. Well,
hopefully the world will agree on the carbon price then.
that could be a good time. I think we were a few minutes past our end time. Is that correct? We were having so much fun.
Yes, we are a few minutes past.
So I want to just thank everyone for participating today, and of course the panelists for their sage advice. But really, these questions are really quite good. There were some requests for early on for some of the slides. I think they'll be posted somewhere on the ACEEE website. But also just keep in mind that fingers crossed, in the not too distant future, this roadmap that we've been discussing, DOE roadmap for industrial decarbonization, will be published. It'll be publicly available, and all of the gory details will be in this roadmap report. So you'll be able to have a referenceable information and document. So, but thanks everyone for participating. Ed, did you have any final words from ACEEE?
I guess I would say that I saw lots of energy on the topic. So tune in tomorrow, where we'll have an opportunity to dig a little bit more into different aspects of this topic. several good topics tomorrow that will touch on this the same area.
All right. I guess with that,
Thank you,
unless there's
everyone.
anything else, thank you for attending, and have a wonderful rest of your Wednesday.
Thanks, everyone.
Thank you. Yeah.
Thanks.
Bye.